So, welcome back friends. Okay, we were looking at deriving the formalism of deriving Dyson series and using Green's functions methods. So, what we asked the question was essentially what happens if the how do you derive the propagator in the interaction if the in an interacting theory essentially, and we considered electromagnetic interactions. We all know what the Lagrangian is for the electromagnetic interactions, the QED Lagrangian, which has been written several times in this lecture series. Okay. So, anyway the Lagrangian I will write it down, it is I del slash minus m psi minus 1 by 4 f mu nu L is equal to, and d slash is equal to del slash plus I e a slash, okay, minus I e a slash. Okay. So, this I e del slash is the one which we wrote down, and the equation of motion is just removing one psi, and it gives me this particular fashion essentially. So, in terms of this one, and when you try to solve this essentially in analogy like what we did for the wave function, okay, in analogy like what we did with the wave function, you try to solve it in this fashion, in the same thing as like what we did with analogy with the wave function. In the wave function case, we saw the difference between psi 0 and psi 1 essentially, same thing we try to do with Schrodinger equation or with the Klein-Gordon equation. In the case of Dirac equation also we will do the same thing, one with the interaction with the delta function source and another as a delta function source without the interactions, and then from this you can write perturbatively that the series perturbatively that SF prime can be written in terms of SF of x minus y plus I, because this also has to be taken on the right hand side, SF z x minus z a times z. Again you end up having, because this entire thing goes on this side, SF prime x minus z essentially. Now you solve this step by step and you will see what you get is that this is called the Dyson equation, and then you can do it side by side, step by step in the following fashion. You can write it in terms of a series and you solve it for each insertion of the interaction essentially. With one interaction you get this equation, with two insertions of the interaction terms you get this particular equation, and so the interaction propagator can be written in this particular fashion. Now remember, this is a Dirac propagator, and you can do the same thing for the wave function and also for the photon propagator also you can do the same thing. The photon propagator also you derived it, but for the free particles. Given all this, now you can reinterpret this entire thing in terms of this interpret that in terms of this simple diagrams essentially. These are nothing but your Feynman diagrams, but now at higher order essentially. So, SF total will be equivalent to SF 0 times an interaction at x1 with x, this is in position space, and in this particular fashion you can write it down. Now you can do the same thing with wave functions and so on, and propagators and the couplings also. Okay, you can do the same thing, but now what you want to do is, if you write it in terms of momentum space, you can explicitly write them down in terms of momenta. Essentially you can think of some photon coming out, and in momentum space you can think in terms of a photon coming out and being absorbed at another point, and so on. So you can write down several photons coming at different, so you will solve this in completely in momentum space essentially, though I wrote down position variables, but you typically solve it everything in terms of momentum space. Now remember, these are virtual particles, so the momenta is not specified, they can take any momentum they can take, and this will lead to problems with like renormalization and regularization, which we will address in a second in the coming lectures. In addition to the propagator, you also have the wave function, the external lines, which may have these corrections, or also the propagator of the photon, and also the coupling constants. Essentially the coupling constants also will have corrections. The coupling can also be modified in the presence of interactions. We have only taken the tree level coupling, but the corrected coupling would be completely different essentially. So what does the Dyson series show? The Dyson series shows that the computation using the Fuchs-Green's function method is equivalent to using Feynman rules to calculate process order by order in perturbation theory, and in terms of without the full second quantization or quantization etc., without full meaning we can solve them using just the Feynman rules, at least at the tree levels essentially. If you know the Feynman rules, you can compute without knowing. So this puts on a firm footing that if I know the Feynman rules, I can compute everything without knowing quantum field theory or without knowing second quantization or any of these things. This is the important point of the Dyson series, which has been done using relativistic quantum mechanics. So you are not having the full axiomatic quantum field theory of the everything essentially. Okay, the Feynman rules become so powerful that you do not need to know the full details of the quantum field theory or something, and this has been established by the Dyson series. Okay, so you get the same results if you are computing, and order by order you can calculate essentially. So this is what I wanted to establish, the main result of this course. Okay, this is what I wanted to establish for you, and I think this is the this is the takeaway for you for your course. Of course, when you go to the next level of courses on quantum field theory 1 and everything, which I hope I will give in the next year, okay, which you will see that how this all falls in place in a quantum field theory with this either with path integral integration, path integral quantization, or with canonical quantization, how everything falls in space, where we will derive the propagator in a different fashion and so on, so essentially. So good. So we are now reached the point that we have convinced ourselves that we can calculate things using just Feynman rules, forget about everything else essentially. So we will start writing simple process in QED. Simple process in quantum electrodynamics. So for this we will start again with the quantum electrodynamics Lagrangian LQED is equal to, this is what I promised you in the first class or few classes earlier, that we will do simple process in quantum field theory. So what we have established that is that without knowing the full knowledge of quantum field theory, you can calculate things. Okay, this is I think there is a very famous statement supposedly said by Feynman. Suppose he has said that shut up and calculate without asking questions. So this applies to that essentially. You do not need to know the full formalism involved in quantum field theory 1 essentially, which is second quantization and so on. So those are all important. I am not saying to understand the subject, but to calculate scattering cross sections, what this entire thing tells you that if you know the Feynman rules, you can calculate scattering cross sections. But quantum field theory is just not calculating cross sections. Okay, that is sufficient using knowing Feynman rules and using relativistic quantum mechanics. That is the point of this course. That the point of this course that if you know Feynman rules, you can do computation of cross sections. Okay, you do not need the full quantum field theory thing, because this is what is proven by Dyson and we have seen the Dyson series. Now if you want to learn quantum field theory beyond computation of cross sections and everything, that we read quantum field theory essentially. Okay. So now let us look at simple QED process essentially, which is psi bar. The Lagrangian is given by this particular fashion. Okay. Again the interaction is QED is a theory of an electron and a photon. Okay. QED is just a theory of electron and photon. Okay. That is all it is. It is just a theory of one electron, one photon. Electron means here electron as well as positron, both of them are there essentially, and then you have a photon which is a electromagnetic field essentially, the electromagnetic field. Now now let us write down the Feynman rules for the QED. The Feynman rules again start with the vertex. We started with the vertex yesterday. Okay. The same thing, we start with the vertex. This vertex, the QED vertex, which is again given by this particular fashion, in this particular thing, this is equal to psi bar I del slash minus E slash E. You see the interaction term is psi bar gamma mu psi. So psi bar gamma mu psi, the current is psi bar gamma mu psi. So if you remove the vertex fraction is the coefficient of the multiplication of the wave functions. Is this vertex component is nothing but the coefficient of the multiplication of the wave functions. So that is given by minus I e gamma mu. This is your vertex function essentially, and then we had to define how a particle comes in and how a particle goes out. Okay, we had to define what are the wave functions for the incoming and outgoing particles essentially. This is so incoming electron particle is a u wave function essentially u of Ps. Okay. Incoming electron has a wave function which is u of Ps, u of Ps, P is the momentum, S is the spin. Okay. Outgoing electron, meaning from here it goes out from the vertex, outgoing, this is incoming. So outgoing is u bar of Ps. For the antiparticle it has the same signature but with an opposite sign. It is incoming, incoming antiparticle is V bar of Ps. Antiparticle outgoing is V of Ps. Antiparticle outgoing is V of Ps. Remember the antiparticle the sign of the thing is always opposite in direction essentially the particle. Okay. Then photon propagators. Okay, the photon propagator is minus I eta mu nu by q square. The fermionic propagator, which contains both particle and antiparticle wave functions as projections as we have seen, is p slash p square minus m square. So, these are your first QED Feynman rules, which you should know essentially, which you should know, which you should remember essentially, which you should remember, and these are all read out from the Lagrangian essentially, and this just can be done just by reading out from the Lagrangian essentially. With this now we are in a position, okay, to do some simple calculations essentially, okay, simple calculations. When I say simple tree level, simple meaning QED process, let me not say call it as simple because it may lead to some misunderstanding, okay, what I mean by simple essentially. So, these are the QED process and we want to calculate it with so one of the first process is called Compton scattering. Okay, which is E gamma going into E gamma. So, E minus, so E minus gamma going into E minus gamma. This is a scattering process between two electron and a photon and an neutron and a photon. The second important thing is Bhabha scattering. So, Bhabha scattering is E plus E minus going into E plus E minus. Then the third one is called molar scattering, which is E minus going into E minus E minus. Fourth one is called pair annihilation. Is E plus E minus going into gamma. Fifth one is called pair creation. Which is the reverse of that. Now, there are various things which we won't discuss properties actually. Some of these things, meaning like there is something called the crossing symmetry and so on, so which we are not discussing in the present lecture series, which also play a role, which tells you that all the amplitudes are not completely independent. One of the all the amplitudes are related to each other, and say for example molar scattering and Bhabha scattering could be related to each other and so on. So, there are these things, but for the present what we will learn in these lectures is how to draw the Feynman diagrams for each of these process, okay, systematically, and try to compute for at least one of the diagrams for each of these processes essentially, or at least for one of the process. We may not be able to compute for all the process, okay. For one of the process we will start drawing essentially. The most important one is the Compton scattering essentially. So, Compton scattering is E minus photon going into E minus photon. Okay. What is it is nothing but photon interacting with an electron essentially. So, let us fix let us try to draw the diagrams of this particular process essentially. Okay. So, one of the things which we have to see is what are the diagrams for the Compton scattering. So, what are the diagrams for the Compton scattering? Let us draw the diagrams for the Compton scattering in the fashion below essentially. So, we have there are two classes of diagrams like S channel and T channel. So, let us draw these diagrams here. So, there is an electron field and a photon field comes in, photon field exchange, electron field, photon field. So, time is in this direction. So, now we can say P1, P2, P3, P4. Okay, this is time. Now, photons can be exchanged on this direction, essentially the photons can be exchanged, there is nothing problem with them. So, in this case you can have the vertex which is coming with the so in this case the this is called an S channel diagram. So, this is an S channel diagram. Okay. Now, what is the other diagram? Is there any other diagram? The photons can be exchanged, right? Essentially, you can exchange both the diagrams. So, you can have so one of these things. So, in this vertex you have P1 plus P2 going into this, but you can also have P4 minus. If I exchange the photons on both sides, say for example P1 the incoming photon and the outgoing photon, because anything this is a possibility. So, what will happen is P4 minus P1 will become, and the other one would be P2 minus P1. So, the diagram I am drawing would be of this type. This photon would be the P4 photon. So, the vertex here would see a photon of the final state essentially and interacting with the initial state, which is scattering with the initial state, and here this would be P2. So, if we exchange the momenta, we can exchange the particles, or you can exchange the momenta. So, this would mean that your momenta exchange essentially is a T channel diagram, or it depends on the notation, but in some cases you can call it as the T channel, in some places you can call it as the U channels essentially. Okay. So, the difference between these two will be this thing, okay, depending upon your notation. So, these are the two diagrams which contribute to the photon Compton scattering essentially. Okay. Now, you can try to solve this thing. Now, there is one more thing which I have failed to mention before going further, is that what is the wave function of the photon essentially. What is the wave function of the quantum photon? The photon wave function, if it is an external line, okay, the photon wave function is nothing but the polarization vector essentially, polarization vector of a direction. The photon wave function, okay, is nothing but the polarization vector essentially, the external photon incoming. If it is outgoing, it will be epsilon bar essentially, epsilon bar. Okay. So, or minus p or whatever it is essentially. So, if you want to take the photon wave functions, so they have to be either epsilons, or they can be taken with the epsilons essentially, or epsilon primes essentially, or either of them. They are the final state polarization will be the same essentially. There is a polarization vectors epsilon prime for outgoing essentially, incoming or outgoing essentially. These are just polarization vectors of the photon. The photon wave function is just now there are certain things with the photon. The photon is massless. It has only two polarizations possible. So, all massless particles of spin 1 can only have two polarizations. So, this is a general theorem essentially, and this we know, okay, and this also leads to is equal to 0. It is always longitudinally polarized, it is always it is always transverse polarized essentially. So, k mu epsilon mu is equal to 0, k mu epsilon mu is equal to 0 essentially. So, there is no longitudinal polarization. As it is massless. Okay. Now, we can calculate the differential cross section for this particular thing. I think we can calculate the differential cross section by using the Feynman rules essentially. So, you can actually calculate the Feynman rules using, so let us take this diagram, okay, one diagram, okay, I will show you how to calculate for one diagram, and then we can do the same thing for the other diagram, and then you can calculate the final cross section essentially. So, let us start with one diagram. Photon P1, P2, Q, P3, P4, Q is equal to P1 plus P2. Okay. So, we start with each of them essentially. So, we start with let's start with the so there is a vertex here. In this vertex you have P1 for coming in. So, incoming is given by U, IM is equal to U, IE U of P1 times, let me write explicitly essentially, IE gamma mu, then epsilon of mu of P2 times P slash Q slash plus M by Q square minus M square times, so let me write it neatly so that you can see it, and then Now u bar should come essentially. So, this is epsilon mu of P4 I e gamma nu. This is not so let me put some other index here essentially. I e gamma nu u bar of P3. So, this has to be your total cross section total amplitude for one diagram. Now, you have to put in q is equal to P1 plus P2 into this, and that gives me one amplitude essentially. So, that gives me one diagram, okay, amplitude of the diagram. So, I m is equal to u of P1 gamma mu q slash is nothing but P1 plus P2 slash plus m by P1 plus P2 plus m square epsilon mu of P So, this is not this is one essentially, this is the first diagram. So, we call it as the first diagram. Similarly, you also have M2 coming from the second diagram, and the total is equal to I m is equal to M1 plus M2. Total is equal to I M1 plus M2. Now, you have to worry about the symmetry factors, whether there is a difference between them or sum between them. Okay. There is a symmetry factors and everything. There are also the trace sum rules and everything which you have to calculate and so far and so on. At the end of the day, when you do these integrations and everything, it will come out to be that this cross section will end up being some factor which is proportional to cos theta 1 minus cos theta essentially. So, this entire cross section will end up being if you write it in terms of d sigma by d omega using the trace theorems, there are several things which you have to do essentially. This putting all this together, this will end up, the cross section ends up being d sigma by d omega of alpha. Compton scattering would be 4 m square of epsilon prime in the limit essentially in the low energy limit. P goes to 0, in the limit P goes to 0, this will become essentially the product of epsilon bar, or I used epsilon prime I think, epsilon prime the outgoing momenta whole square. So, this will be equivalent to the Thomson scattering essentially in the low energy limit. I will also write the full form in the coming lecture, but this is this ends up being, this is also proportional, the d omega part will be proportional 1 minus cos theta, the d omega part. There are details which I am omitting now because lack of time, but I wanted to give you a flavor that at the end of the day the differential cross section ends up being equivalent to the Thomson scattering essentially. That, okay. So, this is what you should remember, that in the limit p goes to 0, it becomes alpha square by 4 m square epsilon by epsilon prime square essentially, where epsilon are your polarization vectors of the photon. Now, we will revisit it essentially in the next lecture, and then we will go through some more details of the Compton scattering before going to, and we will draw the diagrams for the other ones just for practice. And then finally we will talk about the difficulties in renormalization. We will not do all this process in detail because we will not be able to complete all the process. Okay. We will try to do one by one some Feynman diagrams at least, and the details how to do these calculations are left as an exercise, how to do the trace formulas and everything essentially are left as an exercise. Okay. But this just to give you a flavor of how these calculations are done. Okay. I will stop now, okay, and thank you very much.